What are we trying to do with Riemann sums? We're estimating with rectangles. We find the area of each rectangle, adding them all up. How do you find an area of a rectangle? Height times width. So there's the height, there's the width. I'm going to name these rectangles K. So what in the world do I mean by K? When K is 1, I mean I'm on the first rectangle. When K is 2, I mean I'm on the second rectangle. When K is N, I mean I'm on the last rectangle. And if I pick some random rectangle in the middle and I don't want to say which one I'm really talking about, I can call it K. So K is whichever rectangle you are currently talking about. Okay, so here we go with our Riemann sum notation. What does a Riemann sum do for you? It estimates the area under a curve between 2 points A and B. So A and B here are constants. They're part of the setup of the problem. They do not ever change in a single problem. Okay, so A is always whatever it is right here. If I talk about a point over here, this one's still A. I just have to talk about how far from A it takes to get there. All right, so now we took our area, we divided it up into rectangles, and these little points where I actually made the divisions from one rectangle to the next, they're really important. They're on the x-axis and they have a special name. Grid points. All right. So the grid points are the things that tell you where you split up the rectangles. So the very first grid point is called x sub 0. Why they started at 0, I'm not sure, but they did. And that's the same as A. And then the grid point between the first and second rectangle is x sub 1. Between the second and third rectangle is x sub 2. Third and fourth rectangle is x sub 3. All the way to the end where the last grid point is x sub n, and it's the same as B. Sometimes these grid points are also the x values you end up doing in the problem, but sometimes they are not. So we want to think of them as different things. Okay, so what do I mean by x values that you end up using in the problem? So when you actually go to find an area of a rectangle, we need to be able to find the width, which we're going to talk about. We're going to call delta x. That stands for change in x, and what we mean by that is how much x changes from one side of the rectangle to the other side. So what do we just mean width. All right, and then what we need is the height, and the height part here is a little bit tricky. So if I drew in, this is my rectangle number K right here in bright pink. So let's pretend I'm drawing in rectangle number K, and if I draw it in like this, is that an acceptable rectangle K? No, what's wrong with it? It's too high, it's too tall. Okay, well, you wanted shorter. Let's see if we can do shorter. How about that one? Is that good? No, what's wrong with it? It's too short. Okay, so how high am I supposed to make it? It's got to cross this function here somewhere. So it could be here, it can be here, it can be somewhere in between, like there, or the one where they actually give you. But it has to cross that function somewhere. So how do I write that? Well, if it's crossing the function, it should have the same height as the function for some point on that function. So like right here, this point on the function is some x value comma some y value, and it's the same height as the rectangle. And height is it the x value or the y value? Y. Okay, so the height of the rectangle, you're telling me, should be the y value for some point in my function. All right, so the point that it's the y value for, we're going to call this point x sub k star f of x sub k star. Now this may seem like an awful lot of notation for no good reason, but there is somewhat of a reason. All right, so let's break it down. It's x because it's an x value, right? And then what do you think the k is telling you? Which rectangle you're using it for, right? So you're using it for rectangle number k. And why don't we just call it x sub k? Why do we need a star? To make it not this point right here. We've already used x sub k to mean something, unfortunately. So now we need a star. And this x sub k star is a very different thing than x sub k, and it's also a different thing from delta x. And if you like little hats, I've seen people put little hats on them instead, or little bars on top of them, or you need something that's more than just x sub k. Your book does stars. So now if you want to find a y value, you have to have an x value. We're going to call it x sub k star, and then you're going to stick that into a function. that y value will be the height that you'll use for your rectangle. And you already told me I'm supposed to take that height, multiply it by the width, which we call delta x, and that gives me the area of rectangle K. Do you agree with that? All right, and then if I want to find the area of the whole thing, I should add them all up. So I'll take sum x sub k star times delta x for k starting at rectangle number 1 and stopping at rectangle number n. Does that look familiar? Maybe? This is the definition out of your book of a Riemann sum, right there. The sum k goes from 1 to n, so we're adding them all up of f of x sub k star. So x sub k star is the x value. We plug it into f. This is the height. And then we multiply by delta x, which is the width. All right, so we need to know two things before we can actually do an example. We need a formula to find delta x and a formula to find x sub k star. So we'll start with delta x maybe, because that's a little bit easier. So delta x, what do you guys think? Let's skip over here to this one. So I'm trying to figure out how big delta x should be. One of the nice things is you get to assume that all of the delta x's are the same. You can actually do Riemann sums where each rectangle has their own width, and then things are even more fun. But if we assume they're all the same, then they have to live in this world between A and B. So how far is it from A to B? B minus A, beautiful. And if I want to split that up into n equal pieces, what should I do? Divide by n. There you go. There's your formula for delta x. That's not so bad. So note then, once you found delta x, it's constant for the entire problem. Now the fun part. That is the x of k stars. This does depend on k. So, you know, you're going to be plugging in a different x value for each rectangle. So this should be a formula that has to do with k. And the formula is, if you want right endpoints, okay, so we got right, left, midpoint, and generic, and maybe we should talk about what in the world that means first. So this is one of those beautiful pictures from your book. How many of you have used the beautiful pictures out of your book? You should do this. If you go in my math lab and you click on your book, you can actually go in there and play with it. So for example, here I have left Riemann sums. I can have lots of rectangles. I can have a few rectangles. Figure out what in the world's going on. And what I want you to look at when you do this is I have right here, these numbers are my grid points. They're going to stay the same. But these ones down here are my x values. So talk about lots of notation. This point right here has 3 names. We call it A because it's the farthest thing to the left. We call it x sub 0 because it's the first edge of the first rectangle, so it's the first grid point. And we call it x sub 1 star because it's the x value we're going to use to plug into the function for the height of the first rectangle. And all of those things mean the same darn point. What do you think of that? Are you on board with me so far? Okay, so watch what happens to those x values if I switch. All right, so I'm doing left Riemann sums. If I switch to right Riemann sums, watch those x of k stars. What happened to them? They moved over one, right? And what happens if I go to midpoint? They move to the middle. And then if I do generic Riemann sums, I can put them wherever I want. All right. And then once again, you do better if you have less rectangles or more rectangles. Which is better? More is better. Okay. And does it matter which of these ways you do it? Will you get the same answer if you do left or right or midpoint? You will not, because these are estimates. You will get close to the same answer because they're all estimating the same thing. And the more rectangles you have, the closer those answers will be. We have formulas for x of k star depending on which one they tell us to do. If they tell you to do right, it's A, the original left edge, plus k, which rectangle you're on, times delta x, the width of those rectangles. If you are doing left, it's A plus k minus 1 delta x. And if you're doing midpoint, it's A plus k minus a half delta x. So that's just the formula. You need to know it. To give you just a little bit of an idea of where it's coming from, if we go back to this picture, where did my picture go? Oh, forward. If I go forward to this picture, and we look at this picture again, if I'm doing right Riemann sums, say, which of these grid points am I going to plug in for my first rectangle to find the height? X1, okay. So this is my point. If I want to figure out its value, I start at A, and I skip over 1 delta x. So I end up with A plus delta x. Seem reasonable? Maybe? Okay. So for the second rectangle, I need this point right here. So I start at A, and I go over 2 delta x's. So I'd have A plus 2 delta x's. For the third rectangle, I want this point right here. So I start at A, and I go to the right 1, 2, 3 delta x's. So A plus 3 delta x. Do you see a pattern? Can you tell me what rectangle number K's x value should be? A plus K delta x. So maybe I should put it on here. There's rectangle number K, A plus K delta x. So that's what we mean when we have that little formula that gives us those points. Okay, let's make this more kind. All right, so here we are, example time. Our example is, estimate the area under f of x equals x squared plus 2 on the interval from -2 to 3 using 5 rectangles and write Riemann sums. Now for the fun of it, or because I think it will help you, we're going to do this 3 different ways. First, we're going to do it the novice, before calculus, I'm in first grade type way. Second, we're going to do it the way that you probably maybe sort of feel comfortable with right now. And then we're going to do it the way you're supposed to do it with all of the algebra and all of that stuff in the sigma notation. Sound like a plan? Okay. So way number 1, back to first grade. I give you this beautiful picture. I tell you to tell me the area of all those rectangles combined. What are you going to do? Yeah. I'm going to count them. I'm going to find the area of each rectangle from the picture. So something like 1, 2, 3. There's 3 for that one. 4, 5, there's 2 on that one. 6, 7, 8, there's 3 on that one. 9, 10, 11, 12, 13, 14, there's 6 on that one. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There's 11 on that one. And so if I add up for all those rectangles, I add them up, I get that 25 again. The answer should be 25. So if only we could do that on the midterm, right? That would be good. But that's all we're going to do. We're just going to do it with a lot more formulas. Questions about that part? You get it? Hopefully. We're okay there. Okay. So now we need to actually calculate the areas of all these rectangles using just the information they gave us and not using the picture. All right. So here's the picture-free method. Okay. So what we're going to do, we need to figure out all these things we're supposed to know. So A, B, N, f of x, and delta x. These are all parts of the setup of the problem that we need to find before we can even start. So can you tell me what these things are? What's A? -2. What's B? 3. What's N? 5. N is the number of rectangles. F of x. X squared plus 2. And delta x. How do we do that again? Yeah, v minus a over n, so 3 minus -2 over 5, which happens to be 1. Okay. Are we good about that part? Now this delta x is going to end up being important, so don't forget it, even though it's up here at the top. Okay. So now what we need to do is calculate the area of every rectangle. So what I'm going to do is make a chart. And I'm going to start on this chart with a column for K, because K, remember, tells us what rectangle we're on. We'll make a column for directions there, and then we're going to have rectangle 1, rectangle 2, rectangle 3, rectangle 4, and rectangle 5. Now what we would really love is to know the area of each of these rectangles. So that's the last column over here. But in order to find the area, we need to know the height and the width. We already know one of those. Which one do we already know? Width. We know delta x, it's 1. So we need to know the height. And in order to know the height, what do we need to know? Well, we know the function. What are we going to plug into the function? That darn x, so we'll just say x value. X sub k star. Okay. So remind you that k is the number rectangle we're on. That x sub k star, since we're doing right Riemann sums here, is a plus I delta x. The height is what happens when we take x sub k star and plug it into f. And then the area is what happens when we take the height and multiply it by delta x. Seem reasonable? Okay, we'll do the first line together and then you guys can finish it. So rectangle number 1. That's this one right here. We would like to find the x value we plug in to find the height. So just to make sure we're all talking about the same thing, look at the picture and tell me what the answer to this one should be. What am I trying to find from the picture? What x value did I plug into the function to find the height right here? -1. So this should be -1. So let's try it. Let's actually use the formula that they give us there. So the formula is a plus I delta x. So a is -2. K. What's k? 1, because we're on the first rectangle. All right. And what's delta x? 1. All right. So if we simplify all that, what do we get? -1, just like we were supposed to. Okay, so now we need to find the height by plugging that function into f. And what was f again? That was x squared plus 2. So we want f of -1, which would be -1 squared plus 2, which turns out to equal 3. And if you look on the picture, is 3 the height of our rectangle that we're looking for here? Yes, okay. So now that we found the height, we need to find the area. So we take the height, and we multiply it by delta x. And what is our delta x? 1. So 3 times 1, that's 3. That's the area for rectangle number 1, and that's the area for rectangle number 1 when we count them. So that's all well and good. So the thing to notice is you're not multiplying this column and this column to get this column. You're multiplying the second column times delta x to get the third column. All right, go ahead and see if you can fill out the rest of the chart. So if you're doing it right, you should end up with that 3, 2, 3, 6, 11 down the last column, just like we got when we counted. But let's go on to the lots of notation way of doing this with the sigmas. And this is really important because what we're going to do is we're going to do everything we just did, but we're going to leave the k in there. So instead of actually plugging in a number for each different k, we're only going to have to do all this stuff once, but we're going to do it with the k still in there. And then if we really wanted to, we could go back and fill out this chart just by plugging in the numbers for k. Now this is important because when k runs from 1 to 5, we can write a chart with all of them. But when it runs from 1 to 5,000, we really don't want to, right? So if we do a formula instead, we can get around that with the sigma notation rules. And after the exam, when we do this for n number of rectangles and we don't even know how many there are, our only choice is going to be to do it with the sigma notation. So that's why it's really important to get your head around this part. Okay, so what do we do? Well, all the beginning stuff is still the same. A is still -2, B is still 3, n is still 5, delta x is still 1, and f of x is still x squared plus 2. And now we're going to find all the same things we just found in the chart. So we're going to find first, well, we know k, it's just going to be k. So the next thing we need to find is x sub k star. And the formula, since we're doing right, is still a plus k delta x. And now let's plug in stuff for that. So x sub k star, the x value, is going to be -2 plus, now we leave the k, times 1 for delta x. So it's -2 plus k. That's your x value. How do we feel about that? We okay so far? Okay, so then the next step is to find the height. And we do that by taking our x value and plugging it into our function. So we're going to find f of negative 2 plus k, which is negative 2 plus k squared plus 2. So this is your y value, or your height. All right, and so then the last thing we need is to find the area. And so to do that, we take our f of x sub k star and multiply it by delta x. So we take our negative 2 plus k squared plus 2, put it in big brackets, and multiply it by 1. And that is the area of rectangle K. And if that's the area for one rectangle, how do I find the area of the whole thing? Add them all up. Okay. This is where the sigma notation comes in. I take negative 2 plus k squared plus 2 times 1. That's the area for rectangle number K. And then I add them all up with K starting at rectangle 1 and ending at rectangle N. And this is your total area in terms of sigma notation. So this is a phrase that you'll see a lot in terms of sigma notation. On a homework or maybe on an exam, they'll say, here's a setup, give me what it would be in terms of sigma notation. So that would be right here. Oh, yeah, so let's put in the 5 there. All right, so if I wanted to actually get to 25 from here, what would I do? Yeah, so I got two choices. One is that I can literally plug in 1 through 5 for k. That's what we did before, right? That's what we did with the chart. So we can plug in 1 through 5 for k and add. But there's another way we can do it now. This is the whole reason for doing the sigma notation, because it gives you a second way of solving these problems. What is that? You guys remember what we did for the first 10 minutes? Yeah, we're going to use the sigma notation rules to simplify this down. So we're going to FOIL everything out, which is going to be 4 minus 4k plus 2. Wait, that's not right. I lost something. Plus k squared plus 2. Then I'll combine like terms. 6 minus 4k plus k squared. How are you guys doing up to there? This is just like that example we did at the very beginning. So what did we do next in that example we did at the very beginning? Split it up. Okay, so let's split it up. Sum k goes from 1 to 5 of 6 minus sum k goes from 1 to 5 of 4k plus sum k goes from 1 to 5 of k squared. And now what do I do? Pull the constants out front. So 6 times the sum k goes from 1 to 5 of 1 minus 4 times the sum k goes from 1 to 5 of k plus the sum k goes from 1 to 5 of k squared. All right, so now we have things that we have formulas for, right? And these are those formulas that have all those n's in them. And so we end up with 6 times n, which is 5, minus 4 times 5 times 5 plus 1 divided by 2 plus 5 times 6 times 11 divided by 6. And you put that in your calculator. How do you do it if you have 5,000 rectangles? Because now we do not have the choice of just plugging stuff in unless you want to be here all day. So we have to do everything we just did for the last one, that pro method, but we're going to do it now for a different value, a number of rectangles, for a different n. So this is the other point for doing it again, is to show you what happens if we change n. So A and B are still the same. A is -2, B is 3, but now N is going to be 5,000, and F is still the same. So now we have to recalculate our delta x. It's supposed to be B minus A over N. So it's 3 minus -2 over 5,000, which is 5 over 5,000, which is 1 over 1,000. Feel okay about that? Okay. So the next thing we need to do is find the x value. So that's the x of k star. So that is A, which was -2, plus k times delta x, which is now 1 over 1,000. So this is -2 plus k over 1,000. And this is the thing that would change if you needed to do left. If you needed to do left, you would have a k minus 1 right here, and you'd have a k minus 1 right there. If you needed to do midpoint, you'd have k minus 1/2, and you'd have k minus 1/2 right here. Sound good? Okay. So now the height is we take that thing and plug it into f. So f of -2 plus k over 1,000, which is -2 plus k over 1,000 squared plus 2. And so then to find area, I take the height, -2 plus k over 1,000 squared plus 2, and I multiply it by delta x, which in this case is 1 over 1,000. How are we doing? And that's the area for rectangle number k. So if I want the area for all of them, what should I do? Yes. So I'm now going to do a sum, right? Starting at k equals 1 and going all the way up to 5,000 of all this stuff. There's my height, -2 plus k over 1,000 squared plus 2 times 1 over 1,000. And now I have gotten to sigma notation format. If somebody says write the Riemann sum for this or that, this is also that. So if it says write in terms of sigma notation or write the Riemann sum. That could be another set of instructions they would give you. And that might be something that's fair in a test too. Maybe they don't expect you to actually go any farther from here, but they could give you something complicated until you set it up. So if it just says find the Riemann sum, then you would do this. If it says estimate the area, then you would, yeah, something. You just you're going to have to read the directions carefully.
Is this a good example of
So from here, what we would do is our 1 over 1,000 is a constant, so we're going to pull it out front. K goes from 1 to 5,000. And now I'm going to FOIL all of this. And it is going to look like 6 minus 4k over 1,000 plus 1 over 1,000 squared, no, k squared over 1,000 squared. Does that look right? And now I'm going to split it apart. One thing to be very careful of when you split it apart is that the 1 over 1,000 gets multiplied to everything. So you need big brackets. This part is not so hard, it's just that you have to write so much every time you do it. Okay, so now we need to pull out those constants, and this is where some people get a little wigged out by the fraction. So I'm thinking of it like this. 6 is like 6 times 1, 4k over 1,000 is like 4 over 1,000 times k, and k squared over 1,000 squared is like 1 over 1,000 squared times k squared. So now I can pull those fractions right out front, and I have my 1 over 1,000 big out front, and then I have 6 times the sum k goes from 1 to 5,000 of 1 minus 4 over 1,000 times the sum k goes from 1 to 5,000 of k plus 1 over 1,000 squared sum k goes from 1 to 5,000 of k squared. How are we doing so far? We are almost done, because now all we have to do is replace each of these sums with their formula equivalent. So when we go to do that, we get 1 over 1,000, 6. Now the formula equivalent of the sum of 1 from 1 to 5,000 is 5,000. Minus 4 over 1,000. The formula equivalent of the k part is 5,000 times 5,001 divided by 2. Plus 1 over 1,000 squared. And then the formula equivalent is 5,000 times 5,001 times 10,001 divided by 6. And that we would all put into our calculator.